last left our electrical heroes, our physics heroes. Electrical fields exist. We're not going to do anything else with them. But Q is the magnitude of the charge creating a field. So even a little tiny point charge, a little tiny atom that is unbalanced, that has too many or too few electrons, creates a charge. The magnitude of that charge is Q. And if you think about it, that electrical field, that the force that ends up existing there, well, think about electrical attraction and ions. But okay, moving right along. As this thing goes very, very, very slowly. Okay. This is one more thing that we're pretty much not going to do. So we know that electrical force exists. What's the relationship between force and energy?
Force.
Energy is the ability to do what? To do work. Work is force over a displacement, right. So energy and force are related, yes. Electrical potential energy is the ability of a charge to do work on a particle. So something can get moved by electrical force, just like any other force. And there are all kinds of things that if you go on in physics, you will learn about directions of field, and there are rules about, is it right-hand rule? And I can't remember any of it, but you wrap your hands around the moving current, and the direction your fingers point is the direction of the field, something like that. I don't know. This all assumes uniform field, and we don't care. I know this is very, very detailed. There is not a uniform field if you have two different charges, and there is an equation for that, which we're also not going to use. These are fantastic notes. Okay, this is the first thing here that sort of leads back to circuits. Potential difference. So when you saw the video yesterday, we used an analogy of potential difference being a waterfall, and there being a difference in potential energy between the top of the falls and the bottom of the falls. The electrical potential energy is not something we can really use because it varies so much. So every time the charge changes, the amount of potential energy changes. So what we look at is, it's a ratio of potential energy to charge, and it's called the it's potential difference. It's given by the letter V. Do you want to take a guess what that ends up being? Voltage, yeah. So the change in electrical potential, delta V, is what we end up using again and again. We have to have a potential difference around a circuit or nothing flows. And when a battery is dead, there's no more potential difference. So, and we're dealing all with batteries here because AC is way too complicated for us. Okay, capacitance is, you will be using capacitors when you do your circuits. So capacitance is it's a storage thing. A capacitor is just a little device that stores a charge. It stores potential difference, okay? And the most common type is what's called a parallel plate capacitor. So you have two pieces of some material, typically a metal plate, and there is a gap in the middle, and that gap has an insulating material. Now, air is an insulator. Charge does not just flow through air. Air is actually an insulator. And so just having an air gap is the most common insulator. What this allows a circuit to do is to store energy at some point in the circuit other than the battery. This is also why you can get zapped by something that's no longer connected to an electrical source. If you start tearing things apart, if you're one of these people who want to go to the thrift store and get old electronics and just dismantle them to see what they look like, which is a great thing to do. It's a wonderful way to teach yourself about things. if you've had a device that's been plugged in and you unplug it, so you assume that tearing apart the circuits you can't get zapped, you can, because the capacitors store energy in the circuit. And so capacitors will sort of bleed that storage over time. So something that's been unplugged for days or months with the kind of capacitors you see in like consumer electronics, you're not going to get zapped by that. But there are some big industrial systems that have very, very large capacitors that are capable of storing charge for a very long time. So this is the definition of capacitance. There is a limit to how we would use that. Really what I want you to know is that capacitors store charge and that they're typically made up of parallel plates. When you do your circuits, what you're going to see, it's a parallel plate capacitor, but it doesn't look like a little flat thing. What you will see instead is something that looks like this. Okay? It's a little cylinder. And what that cylinder actually is, they have taken two plates like that, and then guess what they do? They coil it up. So that whole thing, let's see if I can actually draw this. Probably not. So the entire thing has been coiled into a cylinder. And then you have these leads, the pieces that come out the bottom. One lead is connected to one plate, one lead is connected to the other. And what capacitors do is they store charge until it gets to a critical point, and then the charge will bridge that gap, and that allows the circuit to flow. Capacitor. It's one of those words I can never spell. Okay. Yeah, it's the parallel plates are actually folded up into a coil. So imagine a pumpkin roll, and those two parallel plates that are held together by a fixed gap are in essence rolled into a tiny little cylinder, and that's put into this, it looks like a little tin can, but they're tiny. I mean, they're like the size of your fingernail or smaller. You'll see capacitors when we start doing our soldering tomorrow. Okay. Current. This is important because if there's no current, your circuit isn't going to do anything. So when you have a net movement of charge through a medium, like a wire, you can have current come through any conductor. You can have current come through the leg of your chair. You can have current the leg of your desk. You can have current come through a metal rod, a piece of sheet metal, the frame of a car. But when we're talking about circuits, the current's typically going to be flowing from a battery, from a source of potential difference through a wire. And current is actually the rate at which charge can move. So it's the amount of charge that passes through an area per unit time, and it's usually per second. And what is the unit for current? Remember this from your video yesterday?
No.
I is the symbol, but what's the unit? It's the amp. Yes. Good, you can read your notes. I'm impressed. Very clever. Okay. It's the amp. Yes, the ampere. And it's 1 coulomb, which is the unit of charge per second. We're not going to do the sample problem here, so we're skipping that. But you will need to know what current is and that the units are amps. So the unit for current is the amp. Okay. Now, we get to some important stuff here. There are two kinds of current. So current goes from high potential to low potential, just like water flows from an area of high gravitational potential energy to low gravitational potential energy. Top of the waterfall to bottom of the waterfall. All that a battery does, so if you imagine, I'm going to draw a 9 volt because it's easy to draw. What you have are 2 cells. And all of your charge, in essence, is in here. So this is an area of high potential. There's a lot of charge that could fall over the waterfall. This is an area of low potential. Now if you take this 9-volt battery and you connect the terminals, the charge is going to flow from here to there. If you do this across your tongue, you get a little bubbly, tingly sensation because you've got electricity running across your tongue. If you do what we would prefer to do, and you make a circuit out of the darned thing that's longer than, you know, an inch across your tongue, that charge, whoops, I gotta get rid of this, that charge is still going to flow from the high potential to the low potential, okay? And you can make that any length, as, I mean, we get into some constraints regarding loss and stuff like that, but for the most part, you can make that circuit as long as you need it to be, and you can get charge to flow from the high potential side to the low potential side. We can do current as direct current or alternating current, okay? Critical to know this. Critical to know. Batteries can only provide one kind of current. Do you know what it is? Direct. Yeah, DC. Batteries are all DC. So, battery, DC current. And in DC current, the charge just continues to flow. Just continues to flow. One direction, unidirectional, it is direct current. Alternating current is what comes into your house. And in alternating current, you have reversals in the flow of charge. And the frequency of those reversals is given as the frequency of the charge. So typical household current is 60 hertz, so 60 reversals per second. But yeah, AC is what comes into your house. Batteries are DC. Does anybody here? Well, here we go. So charge carriers actually move in DC. In AC, the charge carrier doesn't actually move. So the charge, the electrons don't really move. They just vibrate back and forth. And we measure the frequency of vibration. The standard in Europe is different. If you ever head to Europe, you'll need to take a converter for your hairdryer. And you have a little plug that plugs into the wall, and it'll typically have 2 to 4 sides with different frequencies, because different, and well, they're probably not, Europe's probably more unified than it used to be. In the 70s, my parents traveled with a little plug that had, I think, 4 sides. There were 4 different, and it was basically a bunch of little converters inside that box. So to plug any of our American appliances into a wall, you had to put them through the little converter. Otherwise, you would blow them.
They just have one now.
Is it just a single converter?
Single,
Okay.
Yeah, it's like pretty much like a regular plug.
Okay, so batteries only provide DC. We said that. So in a battery, you're actually moving your charge carriers. You can build a generator that will provide AC or DC. AC is more complicated, slightly. Basically, you have to have what is called a so for people who have, and I don't know of anybody around here who does, people who live what they call off the grid, okay? So you've got a bunch of solar panels on a roof someplace that are creating current, and those have to run, you have to have some place to store that current, because you're not using it as you make it, you know. You're either making a little bit too much than, you know, for your uses at the time, or you're not making quite enough. So people who live off the grid typically have a battery bank someplace. They'll have a battery shed. And they have big banks of marine batteries all hooked together. This is how it used to be. It's changing a little bit. And then that all runs to your house. Well, what's the problem there? All of your nice little American appliances are built to run on what kind of current? AC. What's coming out of your battery? DC. So this direct current has to get transformed, and what you have to put in here is an inverter. And an inverter takes DC and turns it into AC. And then you can run your house on AC.
So AC can go either way?
What do you mean either way?
Like it can go, like direct current can only go one way around a circuit.
DC doesn't really move.
DC,
That's the
okay.
complicated thing. The charge carriers don't actually move.
Okay.
So you still have a flow of electrons, but the points of charge don't move; they just oscillate.
Okay.
Beyond that, ask an electrical engineer.
I remember we like went over DC and AC currents in like 7th grade, and she did not talk about like it like this. I think she said AC currents was like when almost like when there's parallel stuff. Like if there's two, like if there's a different way the electricity can get to something.
All right, so
Advancing.
okay, so tomorrow we will actually do about one period of finishing up the stuff we need to know for circuits, and then we will do some soldering instruction, and then you're going to start soldering tomorrow. So, nope.